Imagine you're building the next viral app. Everything is smooth. But boom, your database starts crawling. You've heard about caching, the magical cheat code that makes everything instant. But here's the thing. Most developers treat caching like a simple on-off switch when it's actually a complex dance of consistency and performance. Today, we're diving deep into why your cache is failing and how to fix it. We often think of caching as just putting Redis in front of a SQL database, but if you don't understand the why behind the how, you're just creating a more expensive way to serve stale data. In this video, we will break down the fundamental patterns, the common pitfalls like the thundering herd, and the architectural decisions that separate junior devs from senior engineers. Let's get started by looking at the bottleneck. To understand caching, we need to talk about the memory hierarchy. Not all storage is created equal. At the very top, you have CPU registers and L1 cache. They are blazingly fast, but tiny. Then comes RAM, where your primary cache, like Redis, usually lives. Finally, at the bottom, we have SSDs and hard drives. The speed difference is mind-boggling. Moving from RAM to a disk seek is like waiting for a pizza delivery versus reaching into your fridge. Caching works on the principle of locality of reference. If you accessed a piece of data once, you're likely to access it again soon, or access something near it. By keeping a copy of that data in a faster medium, we bypass the expensive disk I/O. But remember, speed is a trade-off. RAM is expensive and volatile. If the power goes out, your cache is gone.
There are only two hard things in computer science: naming things and cache invalidation. This is where most developers fail. If you update a user's profile in the database, but the cache still holds the old version, your system is now inconsistent. You have two main strategies. First, write-through. You update the cache and the database simultaneously. It's safe, but adds latency to writes. Second, write-back. You update the cache and sync to the database later. This is fast, but risky if the cache crashes. Then there's the time to live, or TTL. This is your safety net. You tell the cache, delete this record after 60 seconds. But what if the data changes in 5 seconds? You're serving stale data for 55 seconds. Finding the right TTL is an art form, not a science.
Have you heard of the thundering herd? Imagine 1 million people hitting your site. The data's in the cache, so life is good. Suddenly, the TTL expires. The cache is now empty. Within milliseconds, all 1 million users hit your database at the exact same time to fetch the same piece of data. Your database dies instantly. This is a cache stampede. To prevent this, you can use leasing or mutexes. Only the first request is allowed to rebuild the cache, while others wait or receive a slightly stale value. Another trick? Randomized TTLs. Instead of every key expiring at exactly 10 p.m., jitter them so they expire between 9:55 and 10:05. This spreads the load and keeps your database breathing.
What if someone requests data that doesn't even exist? This is called cache penetration. Since the data isn't in the DB, it can't be cached. Every single request for user 999 million will go straight to your database. Hackers use this to DOS systems. The fix? Bloom filters. A Bloom filter is a space-efficient data structure that can tell you if an item might be in the database or definitely is not. If the Bloom filter says no, you don't even bother checking the cache or the DB. Alternatively, you can cache null values with a short TTL. This way, the second request for a non-existent item hits the cache and returns not found immediately.
In a distributed system where you have multiple servers, where does the cache live? Local caching is fast because it's in the same process, but it leads to cache fragmentation. Server A might have the data, but server B doesn't. This is why we use distributed caches like Redis or Memcached. They provide a single source of truth for all your application nodes. However, this introduces a network hop. To get the best of both worlds, senior engineers often use multi-level caching. You keep the most frequently used data in a small local cache and the rest in a large distributed Redis cluster. It's more complex to manage, but the performance gains are massive.
We've talked a lot about the backend, but caching happens at every layer. Your browser caches images and scripts so they don't have to be downloaded again. CDNs like Cloudflare cache your entire website at the edge, physically closer to the user. This reduces the speed of light problem. If a user in Tokyo requests a site hosted in New York, the latency is huge. But if a CDN node in Tokyo has a cached copy, it's instant. When designing your cache strategy, don't just think about your database. Think about the entire path from the user's click to your server's response. Every millisecond you save at the edge is a millisecond your server doesn't have to work.
The biggest mistake: over-caching. Not everything belongs in a cache. If your data changes every second, the overhead of updating the cache might be higher than just reading from the DB. If your data is rarely accessed, it's just wasting expensive RAM. This is where cache hit ratio comes in. If your hit ratio is below 80%, you need to reevaluate what you're storing. Also, beware of big keys. Storing a 10 megabyte JSON blob in Redis will block the single-threaded event loop when you try to retrieve it, slowing down everyone else. Break large objects into smaller keys. Caching is a scalpel, not a sledgehammer. Use it precisely.
So, here is your caching checklist for your next project. First, choose the right strategy. Write through for consistency, write back for speed. Second, always set a TTL, but randomize it to avoid the thundering herd. Third, use Bloom filters or null caching to stop penetration attacks. Fourth, monitor your hit ratio and evict keys that aren't pulling their weight. Caching isn't just about making things faster, it's about making your system resilient. A well-cached system can survive traffic spikes that would normally melt your infrastructure. If you master these patterns, you're not just a coder, you're an architect.
Thanks for watching. Caching is a deep topic, and we've only scratched the surface. If you found this helpful, hit that like button and subscribe for more deep dives into system design. What's the weirdest cache bug you've ever encountered? Let me know in the comments below. Whether it was a stale data nightmare or a Redis cluster that went rogue, I want to hear about it. Until next time, keep your latencies low and your hit rates high. Happy coding!